So thank you for this opportunity. So I was asked to, we were asked to participate, and the session that we were asked to speak in is the cognitive systems session. And it was pretty nice that we wondered who would speak and what we'd talk about. And my team, so I come from Ericsson Research, and the Ericsson Research in Bangalore is small, about 7 people. And what we do is we work on a bunch of things. One of them happens to be what we call the management of complex systems. Okay, so complex systems to cognitive systems, right? And the connection is that piece that you see there, knowledge. So what I'll talk to you about is what cognitive systems are, how they make sense, how it ties in with this thing called knowledge. And you'll see a lot of words here that you would have heard in the morning, perhaps heard yesterday, and perhaps you'll hear in the other talks in this track. So I'll talk about, I'll try to give you a general introduction to cognitive systems or artificial intelligence, and talk about something that I like to call the savant syndrome in AI, and where we go beyond it. And I'll give you an idea of how these systems are architected. The idea is that you'll be able to see how different things like the vision stuff and the speech stuff, how it fits into this. And then I'll talk about the stuff that we work on, which is knowledge, a couple of things about knowledge, and then I'll summarize. So this is somebody that many of us here would be familiar with. So this person is Alan Turing. And in 1950, he sort of made this statement in one of his papers that's titled there. He asked the question, can machines think? And the way he formalized it a little more was saying, will they do well in an imitation game, imitate a human being, right? And sort of he said, here's the scenario. This guy C is an interrogator. He's a person who asks questions. And then on the other side, there is either a person A, a machine A, or a person B, and he has to figure out whether he's talking to a human being or if he's talking to a machine. And if a machine can, most often than not, fool him to believe that he's talking to a human being, and that's it. So you have achieved artificial intelligence. This was sort of his very nice, simplistic definition of machines being intelligent. Just to get over the fact that you can hear people, you can hear voices, but may not have good computer synthesized voice, he said, let them talk in text, right? So you'll type something and send it across, and that person, would type something. So, barring all that, getting out of those media issues, he said, so in the language terms, right? And he said it's about aesthetics. So, a computer talking very flatly to you would not make sense. It's about aesthetics. It's also about emotions, right? So when you talk to somebody, you talk not just about facts and figures. Indeed, he said it's not about facts. It's not about somebody telling you, yeah, I know the height of this Everest, or I know the deepest point in the ocean or something. It's not about that, right? And it's not about doing computations fast. So this is interesting that Alan Turing, when he proposed this, he thought of these things. That was very nice. And so people have been trying to do artificial intelligence. It's got a long history. But in 1991, there's this prize called the Leibniz Prize that was instituted. And this was a prize to be given away to the person who would build the first artificial intelligent machine that could fool an interrogator, right? So it was based on exactly that model. Perhaps the version varies a little bit, but interestingly, this prize is sort of, you always have a first, second, third, but nobody has won the grand prize yet. Not surprisingly, right? So it's good that our standards are high, so we feel happy about that. But what we have done is we have built machines to do things well. So 1997, we know that Kasparov was defeated by the Deep Blue, right? And so that was a bit of a shock, definitely a big shock at that time, right? And right now, it's no longer a shock, right? So there's this guy called the Komodo, it's actually a chess engine, and that guy's ELO rating is about 450 more than the best human playing right now, right? So you don't have, nowadays you have conferences where you have these chess matches where the machine plays another machine, doesn't play a human. Also, but the story is not that, it's that rosy everywhere. Only in 2015, the DeepMind project from Google created this computer program that would defeat a human or the champion in the game of Go. So that's another board game, but that's a long time, several years. On the other side, we have this nice story of Watson winning Jeopardy. So we were all very thrilled when this news came out. What's interesting about this is, unlike the two other examples, this is an open domain question, right? This is really nice, right? The computer could not have obviously been fed all this information one by one, right? It's not possible, right? You can create search strategies, heuristics for these games, but what do you do for this? Very nice. So it was a huge sort of victory for artificial intelligence in a way. What's happened after that more recently, right? These are examples. For example, now you have face recognition software. So it's not just about recognizing a face. So you already have seen that your face gets recognized when you upload your photograph, and your friend's face gets recognized, and all that kind of stuff, right? But it's a little better than that. It's more about recognizing the face means recognizing not just who it is or the fact that it's a person, but the fact that the person is happy or angry. So that's a huge difference between recognizing who it is, right? Image recognition is a complicated business, and that means a lot of learning. So it can't be fed. So again, go back to Watson. Watson started off this journey, right? Information cannot be fed in the traditional sense. Knowledge can't be fed, right? It has to learn. So learning has become sort of the basis of a lot of the recent cool stuff that we see. Now, I sort of call this the autistic savant syndrome in AI. So what that means is that you're extremely good at one thing, extremely good at a few things that normal people find very difficult to do, right? So we have humans who can compute pi and all that, right? You just sing out the numbers, the digits of pi. And this guy, apparently, if you've watched this movie, which I did long back, he can count the number of toothpicks that have fallen down on the floor or something like that. So there are people who have these, right? So the human brain is very interesting. So things happen, and then these people are super autistic, super good, but for many things, they just can't emotionally connect with people, right? So AI is sort of somewhere there, right? So you could this nice, real good chess playing machine, right? You'll defeat the world champion, but then, how would you like tea? Oh my God, what does that mean? So that's where we are. So from chess and Go to Jeopardy, I think that there is a big change there that happened, right? We went from heuristics and algorithms and search. So there the programmer has put everything in, little more than that, but at least as a starting point. We went to Jeopardy where IBM, where the Watson machine actually ingested lots of data and converted that to knowledge. It converted that to knowledge. It's interesting. It also had a lot of other stuff like text processing and stuff, but and then we know that Siri can do things for you. We can book stuff by voice. Google Vision, we've talked about that a little bit with the face recognition, and of course Microsoft does that, Google does that. And then you can convert speech to text, which is very nice. Speech to text is important because you can do a lot of these answering machines suddenly, right? And can you do them with high fidelity? That's the question there. And then there's this, I think this is probably the tip of where we are in terms of moving away from the savant syndrome, right? It's about this, so the Japanese government at some point of time, I don't know, not too long ago, decided that they would have too many old people in their society. And they would need to be cared after, but they don't have enough humans to spend time to care after them. That's the situation. It's true with elderly people, it's true with hospital patients. So they wanted to create humanoid computers. So the government actually said they wanted to create humanoid computers that would assist people. So the goal there is to assist and be a companion. So here's this little thing called the Pepper robot. It's actually spawned off many robots, and one of them is this thing called Pepper, which I believe sits in shopping malls and engages people. So engaging somebody is different from saying, if you want this, go to aisle number 3. It's very different. It's about actually having a conversation. Okay? So take Watson, this is a huge leap, right? It's actually about seeing that person and using the technology that does face recognition. Not recognition, but you know what I mean, right? Something different from that, right? Recognizing. So it's about putting all these pieces together. So this robot is about putting together a bunch of different technologies. Of course, not the least of which is, you know, the hands and the movement and so forth. So it's just one part of it. So we went from search and strategy and algorithms and all that cool stuff, what sounded cool, we went all the way to actually having robots happen. And in between, there are a bunch of techniques and a bunch of, ideas that sort of fit into this. And we've heard of analytics. We'll probably hear more of analytics in this track or some other track. We all heard about machine learning. Again, we'll hear a bit about that. And here I am to talk about one thing that you may not hear elsewhere, and that's about knowledge and reasoning. So, and all these things, if you got what I said about Pepper here, you'll understand that the whole story is not about any one of these, right? Remember the idiot seventh, right? Let's go back to that, right? It's not about doing data analytics great. No, it's not about that, right? It's not about doing reasoning really well. No, it's not about that. Take the robot. The robot needs to finally pick up something. So there's an actuation involved, right? That involves a lot of knowledge, a lot of mechanics. It's not about that, right? It's actually about how these things fit together. That's the question. How do these things fit together? And that's the question that is not easy to answer. And that is sort of where people said we'll introduce this new term called cognitive systems, because they were bored that AI was doing the seventh syndrome things. So they wanted to have a new term. So actually the word cognitive systems, if you see it anywhere, just remember that it's just AI renewed enthusiasm to what it should be. So it's not really anything super different. Now I'll spend a little bit about an old paper here in 2004 talked about what an AI system, how do you build it? So I told you integration is the problem. Integration is the problem. How do I integrate? How do I build this system? What should the pieces look like? And like any good tech guy, these guys came out with a nice architecture, and it's still reasonably valid. So it's an old architecture, 2004, but it's very, very cool. Okay, so down there you have something called the environment. That's the place you have to act in. You have to live in the environment. That is what you're evaluated for. That's the purpose of being there. So the system is in an environment. It does two things. One is it takes perceptions from the environment, perceives, and it acts in the environment. Two things, right? Everything is just these two things. So if you put a human being there, fine, right? If you can put a machine there, can a machine do that? What a human being can do. Can it perceive like a human being? Can it act like a human being? Can it actually learn like a human being, right? Learning is probably our greatest ability beyond perception and action itself. So they said that the simplest of AI systems would be these reactive processes or rule-based or shallow reasoning processes, right? So what that means is, without getting too technical, it just means if A happens, do B, okay? And maybe with a lot of, some changes, right, with policies. If A happens, do B, but always remember C should never happen. Like, this happens, do this, but don't fall off the stage, right? Something like that, right? So there were reactive processes. So reactive processes are very good. You can think of a lot of early robotics as based on reactive processes. So if you hit the wall, turn right. Go ahead. If you hit the wall, turn right, right? Reactive process. But a lot of what we do as humans is deliberative. So what does that mean? That means planning. I want to do something. The fact that you want to do something, not react to what's happening, but the fact that you're driven by something else. It's not just reaction. You're acting, you're not reacting. Right? So the deliberate decision-making process. And then thinking, what if this happened? Knowledge is never complete, so you need to have strategies. What if this happened, right? What if I did this in future, would it increase my sales, right? So what if analysis? And then of course we can't really process every bit of information that's coming in, so we as humans have these nice filters that tell us what we should react to, what we should consider. So each of these is a huge field of activity, of research in itself. But the point is, how do these fit together? And then more than all these, right? So we have techniques for planning, right? People, those who are in the planning will know that planning is a very old field. About 30, 40 years of research has gone into planning. People will know that, we have what-if analysis and all those state diagrams and stuff like that. All that is stuff, fine stuff. But what's important is that as humans, we have the capability of seeing something happen, the results of our action, resulting in something, and taking a step back and saying, oh, the next time I shouldn't do this, or I should do this differently. That's reflection. You are thinking about yourself. And that's how you learn, right? So learning is all part of this reflective process. And then, of course, we have memory. And so the architecture says you need to have memory, you need to have goals, somebody needs to define goals. And then I like the stuff on top there. You need to have a persona about yourself. What's your purpose in life? So I'm a robot, I'm supposed to give comfort to this elderly person. That's sort of like a guiding policy. And that has to be part of everything that you do. You just can't learn because, of some immediate gain. Your learning must encompass a persona, your purpose in life. Right, so this is sort of all the stuff in this architecture, and a lot of the technology that we do, in fact, all of it sort of fits nicely into this. And our real challenge is, now that we have developed these individual pieces, can we integrate them, right? And here's another one, that's another paper that came out around the same time. It's some IBM guys came out with this idea that, you can do this architecture where, as long as you monitor the world and you analyze what's coming in, you can plan ahead and you can execute. All this based on some knowledge that you have. You'll actually be able to do something that can take sensor input. Right now we are talking IoT type stuff or robots, and do some actuations in the world. So these would be intelligent systems that would do something. So sort of a trimmed down version of that diagram is what this shows. And then the central piece of this is actually this knowledge byte. So quickly, a little bit about knowledge. Without getting into this slide into great detail, because we have just a few minutes left, what I'd like to let you know is knowledge is sort of your model or your understanding of the world. For example, when a child does something or when you do something, it's because of a certain understanding of how the world operates. It could be physics of operation, it could be emotional interaction. It's about a model of how the world operates. And what knowledge does, and let's not get into this, it's all about creating that model. It's all about creating that model. It should be a reasonably rich model, right? And perception is an important part of that story, right? It's about seeing things. So now I'm talking about vision. It's about surfing the web. Now I'm talking about text processing and analytics, right? It's about looking at IoT data, another kind of analytics, big data analytics, right? And putting that into memory and in a form that it creates a model for you. So every time you perceive something, you're creating a model in your head. You don't have a choice. That's what you are. That's what I am, right? So perception is an important part of knowledge. And currently there's a lot of work about not just seeing faces, but I told you about recognizing emotions, right? And you can transfer this to other fields. So we did well with faces. Can we do that? Can we do equally well with our experiences interacting with others, right? When we interact with others, when we interact with things, when we interact with objects, we are perceiving through our eyes, also ears and nose and so forth, but we have not reached that far in terms of our capabilities. So what can I do to industrialize this? By industrialize, I simply mean, is there a way of absorbing knowledge and generating, absorbing perception, absorbing data, and generating these knowledge models, right? That's called industrializing in my terms, okay? And this is very important. So you heard some people talk about, we can do lots of innovation. I think it was in the VC forum. We can do lots of innovation now because there are nice building blocks available. Somebody said that, right? So this is about creating those building blocks. These building blocks are critical for us to be able to scale this stuff. So an example is that there's a lot of technology that's been put together by a bunch of, I think it was 10 or so college students, and they actually created a robot that could tidy up a kitchen. So this is to show that we're sort of entering the industrialized phase, right? And the real world applications are probably much more complex. You know, as Ericsson, we always think about many situations, the connected world, whether it is from operators or whether it is devices, whether it is meters metering electricity and so forth. But all this is about sensing, and that's why it's very important to be able to elevate the data that you get to a certain level of, you know, value. So value comes from the knowledge modeling of the data, and that's when you can take reasonable action. So it's the stack that you build, the app that you build has a lot of knowledge to it. So that's pretty much what I have. In summary, so cognitive systems is about AI back to its roots, back to what it's supposed to be. It's about multi-domain. It's a lot about learning. It's about integrating technologies and domains. The other thing I didn't talk about is a lot of AI is about integrating disparate domains, right, which we humans can do naturally. And knowledge modeling is an important part. This is about actually having the knowledge in a form that it can lead to action. And it's important to be able to perceive multiple modes of input and be able to convert these perceptions to knowledge. And the move is towards doing this in a fashion that's industrialized. So you can take these building blocks and it's fun to build systems on top of it. So thank you very much.